Problem is from GATE 2015 mathematics paper, question number 46. The problem given is, let P from R power of 4 to R power of 4 be a linear map such that the null space of T is given by the set the 4 tuple x, y, z, w in R power of 4 such that x plus y plus z plus w equal to 0. And the rank of the matrix T minus 4 times I4 is 3 if the minimal polynomial of P is x times x minus 4 whole power of alpha, then alpha is equal to dash. So NPTEL reference to solve this problem is module 7 lecture number 26 with the title Eigenvalues and Eigenvectors of Linear Operators from the topic Linear Algebra by Dr. K.C. Sivakumar. He is from Department of Mathematics, IIT Madras. Even you can watch this reference video using this YouTube link. So now coming to the problem. So if you observe, it is the hypothesis given is, it is given the set, this set as the null space of T. That means it is nothing but the kernel T, kernel of this linear map T. And it is given one more condition that the minimal polynomial of T as this polynomial, and it is given the rank of the matrix T minus 4i is 3. So what it is given that since it is given the minimal polynomial of T is as this x times x minus 4 whole power of alpha, and we know in the minimal polynomial all the eigenvalues of this linear map T has to include. That means when we factorize this minimal polynomial, so we can see the only roots of this polynomial are nothing but zeros and 4. That can be seen easily as 1 is 4 can be seen from this factor and 0 can be seen from this factor. So we can see the only eigenvalues of the linear map G are 0 and 4. So let me explain. Let me write this. So it is given T is from R power of 4 to R power of 4 with null space of T. Null space of T as the set x, y, z, w such that x plus y plus z plus w equal to 0. And this is nothing but kernel T. So from, okay, let me explain what it is given. One more thing, the rank of T minus 4i is 3 and the minimal polynomial of T is given as x times x minus 4 whole power of alpha. And now we have to calculate what is this alpha. So for that, what we do is, from the given hypothesis, we observe the algebraic multiplicity and geometric multiplicity of each of its eigenvalue. And since from the given minimal polynomial, we can see from the minimal polynomial, the eigenvalues are nothing but eigenvalues of T are 0 and 4 only. This can be repeated since it is the linear map is from R power of 4 to R power of 4. So this linear map has to have 4 eigenvalues, but since here we have 0 and 4 only, but so since it should have 4 eigenvalues, the eigenvalues among these two 0 and 4 has to be repeated, but in total only these two will be the eigenvalues, and that can be seen from this minimal polynomial. And it is given one more condition that kernel T as this set, and that is nothing but the eigenspace corresponding to the eigenvalue 0, and that is since for any x comma y comma z comma w in kernel T, we can see T of x y z w, or can be written like this since T is a map here. T of x comma y comma z comma w is equal to 0, and this is nothing but again 0 times x comma y comma z comma w. So we can see any vector in kernel T is eigenvector corresponding to the eigenvalue 0. So from here we can see for any x comma y comma z comma w in kernel T, we have x plus y plus z plus w equal to 0. And from this we can see x equal to minus y minus z minus w. So why we are doing this is, firstly we will see what is the dimension of this kernel T that represents the eigenspace corresponding to the eigenvalue 0 that defines the geometric multiplicity of this eigenvalue 0. So for this we are calculating the dimension of this kernel P or the null space. So from this we can see x comma y comma z comma t can be written as minus y minus z minus w. This is a single vector minus w comma y comma z comma w. So this can be written as in terms of, so this is y times minus 1, sorry, 1 0 0 plus z times minus 1 0 1 0 plus w times minus 1 0 0 1. So kernel T is generated by three vectors minus 1 1 0 0. Since here y z and w are any arbitrary scalars, so kernel T should be generated by these vectors only, minus 1 0 1 comma 0. These vectors in the sense this is a one basis. Similar to this we can get similar many bases. So but in any whatever the basis we take, we can see dimension of kernel T is 3. Hence from the rank T and nullity theorem we have rank of T is nothing but 4 minus kernel of T, that is nothing but 1. So we have rank of T equal to 4. Sorry, rank of T is 1. And we have the geometric multiplicity of the eigenvalue 0 is 3. So and we have always the geometric multiplicity is less than or equal to algebraic multiplicity. So here we have for the eigenvalue 0, we have 3 is less than or equal to algebraic multiplicity. And since we have already two eigenvalues 0 and 4, so the possible values for the algebraic multiplicity of this eigenvalue 0 should be 3 only. Since if it is if the algebraic multiplicity is 2, then this equation cannot hold, as 3 cannot be less than or equal to 2. And in the same way, if algebraic multiplicity is 1, that is also not true. And in case if algebraic multiplicity of the eigenvalue 0 is 4, that means all the eigenvalues of the matrix T should be zeros only. But here since we have 4 is also one eigenvalue, so the maximum algebraic multiplicity, possible algebraic multiplicity for the eigenvalue 0 should be 3 only, and that can be easily seen from this condition also, rank of T equal to 1. Hence the all of the eigenvalues should be zeros except one eigenvalue, and that eigenvalue is we have 4. So from this we can see, observe, algebraic multiplicity of 0 is equal to geometric multiplicity of 0, and that is equal to 3. And from this we can easily see that, so the algebraic multiplicity of 4 equal to 1. But what is the geometric multiplicity of the eigenvalue 4? For that we have geometric multiplicity of 4 is nothing but 4 is the eigenvalue here, that is nothing but the dimension of the order of the matrix T or linear map T, that is 4 minus rank of A minus 4 I4. And in the problem it is given rank of 4 I4 is 3. So from this we can observe that This is 4 minus 3, that is equal to 1. Hence we have algebraic multiplicity of 4 is nothing but geometric multiplicity of 4, that is equal to 1. That is, in total we have algebraic multiplicity of 0 and equal to geometric multiplicity, and similarly algebraic multiplicity of 4 is equal to geometric multiplicity of 4. So for any matrix, if for each eigenvalue, if we have such kind of conditions that algebraic multiplicity equal to geometric multiplicity for each of its eigenvalue, then the matrix has to be diagonalizable. So we have, since if am equal to gm, that is algebraic multiplicity equal to geometric multiplicity for each eigenvalue, then the matrix is diagonalizable. Hence the matrix, so T is diagonalizable, and its Jordan block will look like 0 0 0 0 0 0 0 0 0 0 0 0 and 0 0 0 4. Why only this is, since in the Jordan block we write the eigenvalues of the matrix T, and since here we have the algebraic multiplicity of 0 is 3, so we have 3 zeros as the eigenvalues and 1 4 as the algebraic, since the algebraic multiplicity of 4 is 1, so we get 4. Since the matrix is diagonalizable, so the maximum possible Jordan block corresponding to each eigenvalue is 1 only. Hence, for each eigenvalue, we have only order of 1 Jordan block. So, this is the only possible Jordan canonical form corresponding to this linear map T. And since for any linear map which is diagonalizable, we know one more condition, that minimal polynomial is linear if and only if T is diagonalizable. Since here for this problem we have T is diagonalizable, that means minimal polynomial is linear. That means x times x minus 4 whole to the power of alpha should be linear. Linear in the sense, when you write as a product of all the factors, that in all the powers corresponding to each factor should be 1 only. Hence alpha equal to 1. What is linear means, when you write the polynomial as this kind of expression, all the powers should be ones only. So here, since for the factor x we already have 1, so for the term x minus 4, the factor x minus 4, the power or the exponent also should be 1. Then only we say this polynomial is linear. So we have alpha equal to 1.